Hi, everyone. Welcome back to the show. Today, I have with me David Bader. He is the Distinguished Professor in the Department of Data Science at New Jersey Institute of Technology. I'm absolutely thrilled to have David on the show. And we're going to be talking about building massive scale analytics. And when I say massive scale, I mean it. So, David, welcome along to the show.
Thank you. Great to be here.
Brilliant. So let's kick off with hearing a bit about you, please. A bit about you, a bit about your background and the role that you currently have.
Sure. So I'm a distinguished professor at the New Jersey Institute of Technology, where I founded our Institute for Data Science back in 2019, and more recently, a Department of Data Science. But the research that really excites me is looking at massive scale analytics. And what that means is once you're faced with terabytes, tens of terabytes and more of data, how do you gain knowledge out of those data sets? And so my research looks at hardware, software, algorithms, and really looking at this to solve real world grand challenge problems.
Exciting. And is that the background you've come from? Have you always been in this kind of space, or have you sort of engineered your career into it?
So, great question. I started out as an electrical engineer and wanting to build computers and high performance computers. And then in 2005, I moved to Georgia Tech, where I founded the School of Computational Science and Engineering. And that was really an effort looking at high performance computing and data science for solving meaningful problems in physics and chemistry and engineering.
Wow.
And then more recently moved into really the hardware and software co-design to build solutions for solving some of the most challenging problems that we see coming out of data science.
Cool. So yeah, so actually you're pretty crafted towards this space, given you started in sort of high performance applications and the like. So, but so in terms of scale, what do we mean? What do we mean? Because there used to be this phrase "big data," and that was a little one of the things about that was scale, of course. But yeah, what do we mean by scale? And what are some of the, I suppose, things in the world that are driving that level of scale that makes it, as kind of broad as it is?
Great question. So for me, scale means what do we do when we have analysts who, in their lingua de franca, that's programming in Python, get to places where they can no longer use their laptops to work on a data set. So the data grows too large, or there are situations where they need to process data sets in motion and do so very, very quickly, for instance, in milliseconds to make decisions automatically. And so what I look at are new algorithms and frameworks and even computer systems that will enable that analyst to productively be able to solve some of these larger applications.
Mm,
And that means data sets that are going beyond, for instance, megabytes and gigabytes, but getting into the range of terabytes and beyond. So what do you do when you're handed a 20 terabyte data set on a couple hard drives and you're asked to analyze it, where
mm.
you no longer load all of that into your computer's memory? Now, the applications that drive this are really increasing and growing. We know data sets are getting larger and larger every year. In fact, there's a tremendous amount of data being generated by social media, by understanding internet traffic, by the population's health. And all of these driving applications result in many data sets. And we may even want to combine different data sets together to solve our problems.
Mm.
So we often focus in areas related to cybersecurity or financial analysis or even human population health.
Right. And is scale important? Does it have to be large scale for data science, or and do all problems require scale in order to properly solve them? Is that your experience?
So great question. And I often say what you want is the smallest big data set that solves your
Mm.
problem. For
Yeah.
instance, we collect a lot of data, but is it all useful for solving the problem at hand? And so the first thing that we want to do is identify the right data to collect and not over collect data for solving these problems. But there are many cases where we want to find a, for instance, we talk about a needle in a haystack where
Mm.
there's one bit of information that's an anomaly in a massive data set that we're looking for. And that is something that's very, very important. For instance, I've worked on problems looking at insider threats within large organizations. And there we want to collect as much as we can to find the one striking action inside an organization where that may be an employee stealing IP or stealing a customer list.
Right.
And we don't want to miss that one event.
Mm.
So in these cases, it may be very important to process all of the information that's available.
Right. So in some instances, so yes, scale is important, I think you're saying, but only from an efficiency point of view, the minimum amount of scale needed to solve the problem. And do you know what that looks like before starting, or is it a case of kind of dialing up, dialing up, dialing up the amount of data, the data sets, the data feeds, the different data structures you bring in? Or is there a kind of, do you normally start with knowing how much enough will be?
Often that's really an art form where a data
Mm.
scientist gets a feel for particular application areas.
Right.
We're building one large scale framework in open source called Arcuda that's a replacement for the standard Python tools like NumPy and Pandas so
Okay.
that analysts can do discovery on large data sets so that they can run their queries productively and in real time on massive data sets to be able to understand what do they need to look at, what information is actually needed to solve their queries. So often you need these large scale frameworks for processing these massive data sets to even explore whether the right ways to analyze it in the future.
Got it. And when I asked you actually at the start about what scale is, you didn't just say lots of data. You talked about kind of complexity of the data. You talked about different data sets coming together. So when we talk about scale and how big the data set needs to be, I think there's also probably a point here about the complexity of either the problem you're trying to solve, the integration or the aggregation of the data that you need, or the data inputs in the first place. Is that fair to say, or really is sort of bigger better?
Oh, you're absolutely right that when I think about scale, there are two axes I look at. One is the processing time, so it's the speed, and then
Mm.
the other is the size of the data sets that I have. Both of these are the costs that will overwhelm my ability to solve the problem on my laptop
Mm.
or on a decent server, where I overwhelm, for instance, a single computer for trying to solve that problem.
Yeah.
And so it's in those cases where I need a faster solution or I need to be able to ingest a much larger data set that scale then becomes a chief concern.
Because you've got different stages of the data sort of pipeline, I guess, the value chain of data, haven't you? You've got the getting it in, the ingestion, as you say. You've got the work to bring it together. You've got the work to analyze it or build for a model to run, and you've got a process for it being produced into a useful data set or set of results. And that can either be an ever decreasing amount of data as you get towards a result, or it can be a ever increasing data set if you're creating new predictions and it's spinning off new insights off the back of the data that you input. So there's kind of, I guess, that scale calculation, for want of a better phrase, for processing time and size of data set, I guess moves and changes as it moves through that data value chain.
That's right. And in addition, often we're looking at large data sets where over time we continue to add information to those data sets
Mm,
and want to continue processing them. So you could think of this as streaming data or batch updates, whether the batches come every minute, every hour, or every day.
yeah.
We may have, for instance, we're collecting the network flow of what's happening in our organization of computer traffic to analyze for cybersecurity threats. And
Mm,
every day we may get a new batch of system logs to add to what we already are holding. And then maybe we want to age off some old data. So
right.
often we need the space and flexibility to continue to update data sets and continue to run, for instance, persistent analytics as part of that workflow that you just mentioned.
Yeah. Now you mentioned sort of scale being beyond that someone's laptop could run. And I think that's sort of like a data scientist view, kind of the world, in terms of, I've got my machine, I want to run some heavy load. Just sort of help me understand that in terms of current sort of how most infrastructure is starting to be set up with quite kind of cloud-based platforms, and a lot of the processing being done, on someone else's computer, let's say on the server, either in the cloud or in a data center somewhere, rather than locally. Is the problem that you like to solve the local version? Is it, I've got the data, I'm going to do something with it, or actually is this a problem that can be applied to the data set in its broadest sense, as in the stuff that's held centrally somewhere?
Right. So often in the enterprise, data sets are held in the cloud, yet the frameworks are very limited as to what operations you can run on those large data sets. For
Mm,
instance, you may have data lakes where you can collect subsets of that data to process locally, but the information stored in the cloud is very hard to run the analytic in place
right.
or to combine different data sets together. So what you're doing is often subsetting and moving those data sets. And there's a real cost for moving data, especially large data
Yeah.
becomes cost prohibitive. It takes a lot of time, and you also need storage for it.
Mm,
In the frameworks that we're building, what we imagine is that the data set is sitting somewhere on, for instance, a backend supercomputer. However, normally you would need a heroic programmer to figure out how to get that supercomputer to work. And that's where we come in. My research team works on designing these analytics so that any data scientist who knows Python could use their libraries on their laptop, say in a Jupyter notebook,
right.
and still have the data being manipulated in a back end on a supercomputer in near real time. And
Right.
so they could be running their analyses for a data set that is held remotely, but yet we have the capabilities to do it in high performance and to do it productively with our data scientists who are still just working in Python that they're very comfortable with.
Yeah, got it. So it's kind of bridging that gap, and the best of both worlds, both large storage in a center, and some of the heavy lifting done there, but also the ability to bring that locally and be productive locally. I get it. What just on that, what other, we talked about scale and complexity, and where that scale sits in the data value chain, but we've got to deal with that. That we need to kind of, you have built some frameworks, and there's some concepts behind dealing with large scale, massive scale data and analytics. So what are some of the methods and approaches that you need to apply in order to handle such big data sets?
Let me give you an example of one module that we're building out.
Okay.
So we have an open source package on GitHub called Arachne, which is the Greek word for spider, and it runs on top of this Arcuda framework that I mentioned earlier. Arcuda is the Greek word for bear, and this is also open source on GitHub.
Right.
Arachne is our library for doing massive scale graph analytics. So often in many disciplines and many types of data science problems, we have relationships between entities, whether we're doing social network analysis or we're trying to analyze patient data or we're looking at cybersecurity traffic. In all of these examples, we often have objects and relationships between those objects. And we can abstract that problem as a graph, yet there are very few, if any, frameworks that can analyze a graph that has trillions of entities in it. So we
Right.
built out Arachne to give users and data scientists the very easy capability to run a large scale graph analytic on these data sets. And for instance, those graph analytics could include simple algorithms like breadth first search or connected components, but we have higher level analyses such as between centrality and triangle centrality. We can find K-trusses within the graph that is telling us more detail about the community structure and even more analytics that are really helpful for getting insights as to what is actually happening within those data sets.
Right. So one of those approach, I think, if I sort of play that back, is to, well, A, use graph databases because of the efficiency, I suppose, it has in running that analytics. Um, is there something about sort of the way data's held, the way data's stored, the way you optimize it, the way we apply logic to it that means you can deal with that, other ways that you can deal with that large scale?
In this framework that I mentioned, the large data sets sit on a back end that could be a cluster, it could be a supercomputer, but a machine that is capable for holding that scale.
Right.
And our secret sauce is an open source compiler from HPE/Cray called Chapel. And
Okay.
this was the compiler that was developed about its origins go back about 20 years, but it gives us a framework where we can highly optimize the data science operations on the back end.
Hmm.
And the user really just has to call the algorithm in the front end in Python. And we're doing all of the complicated optimization with the Chapel compiler to make sure that it runs quite efficiently on the back end. And
Right.
this way, we're bridging that scale. We have our data scientists who may not have had much programming skill in the past, being able to manipulate large data sets on a supercomputer and to do it just seamlessly. So we're very proud of that accomplishment.
Yeah, that's great. Is there any, from a technology point of view, is there something that's required for something different that's required for large scale, or actually is this, commodity hardware, as you talked about before, laptops, but to deal with scale, either kind of that front end part, data scientists interacting, or back end part of data storage and processing, or anything else in between, or either side of that? Is there any technology, hardware, software that's needed in order to drive that high performance?
That's a great question. It's highly problem dependent. So
Right.
there are some use cases where you could run on a very generic cluster on the back end with commodity hardware. There are other cases, depending on the analytics you're running. For instance, these graph algorithms tend to put a lot of pressure on your communication subsystem.
Right.
And there are specialized high speed interconnection networks on these supercomputers that really enable high performance whenever you're looking at global operations that drive your both your memory bandwidth but also your communication bandwidth across the machine.
Right.
And so depending on your application area, you may want to run benchmarks on a few different platforms of the type of analytic you're interested in to see if that specialized hardware gives you a performance increase.
Right. Interesting. I guess you have to run. Yeah, this is all about running tests, seeing what works, because it's the balance, isn't it, of chucking more processing power and hardware at things versus tuning and refining software and the open source frameworks that you're building to get that perfect storm of performance.
Correct. And often it isn't just the number of cores or processors you have, the
Right.
amount of memory that you have available may be a first constraint on your performance, or how much communication bandwidth you have in your network.
Mm.
So it isn't always just having more and more nodes or cores. You
Yeah.
really have to look at where's the bottleneck
The
in the
weakest link.
analytic.
Yeah.
Correct, correct. And
Yeah.
that makes a huge difference because when you're investing your money in the type of cloud environment or the type of infrastructure, you want to make sure you're investing in the right areas.
So here's a question: can the weakest link be the person, the user, who's then interacting with that high end technology?
We hope not. So if we can encapsulate the analytics quite well in these frameworks,
Mm.
then for instance, in my research group, I have just amazing high school students working in my research group that are they're bright, very, very bright, but they don't have as much experience writing algorithms or programming, and they're doing great getting performance out of these systems. So
Yeah.
we've tried to make it easy to use and reliable so that any programmer that knows how to write in Python will get good performance out of this system.
Yeah, lower the barrier to entry to
That's
do that
right.
kind of work. What about the other side? Just talking about capabilities, then, 'cause I wanted to come on to this. So you've got, I understand from the frameworks that you're building, but also I think you're talking more principally about technology should be quite easy to use and lower the barrier to entry and that sort of thing. In terms of building it, though, building this high performance, highly scalable back end and front end, what kind of capabilities have you needed in order to put that together? Because that's not high school students and maybe even early graduates. That's you've been in this game for a long time. That's experience, right? Or is there some specific skills, experience, background that's required in order to build scalable platforms?
That's a great question. I've been in the field for several decades now and have seen the evolution of computer architectures. In
Mm,
fact, back in the late 1990s, I built the very first commodity-based supercomputer using the Linux operating system.
right.
And at that time, I really looked at driving the commodity curves for designing very highly capable systems. I also pioneered the use of accelerators. For instance, the PlayStation 3 was accelerated with the IBM Cell broadband engine processor,
Right.
and that processor accelerated the first petascale supercomputer in the United States. I've also worked with NVIDIA and NVIDIA GPUs to accelerate computing. So the types of skills that we need are really researchers who understand algorithms and matching algorithms to architecture. And
Right.
it's really key to be able to look at those two areas in tandem to be able to influence the architectural designs and to be able to assemble the right infrastructure that supports the algorithms that we want to use in our applications.
Mm. It's interesting that as a kind of most organizations, if I think about the commercial world, that's a kind of team sport that does that. You've got, otherwise you're looking a little bit for the unicorn, and maybe you are it, David. But this kind of like this combination of understanding business outcomes, understanding algorithms, understanding the data, and you're saying, and rightly, I think, understanding the architecture and infrastructure needed, and bringing all those things together and going, right, well, what's going to work to get, it was almost like a graphic equalizer, what's going to work in combination. We can throw more processing power at it, but that's cost money. We can tweak the algorithm, but that requires deep, machine learning knowledge or whatever it might be. So it's that balance, isn't it? I think what you're saying.
That's right. And often the best improvement that you can have is an improvement to an algorithm because that will give you asymptotic gains, and that often will exceed what you can do in architecture. So sometimes simplifying the algorithm is a way to move forward faster, but that's also often a challenge. It takes a lot of thought power to see if you can improve the algorithm.
Mm,
But you're absolutely right. I may be somewhat of a unicorn in this. I've worked with companies like IBM, Cray, Intel, NVIDIA, and many others in the computing industry. And I've been able to bridge between the architecture and the algorithms.
yeah.
More and
Yeah.
more abstraction hides what's happening inside these really capable systems.
Mm,
And you need an individual who's able to look at the entire stack, the entire vertical stack, to understand when I run my data science application, what's actually happening to the electrons
yeah.
down in
Yeah.
these wires and chips.
Yeah, but bringing it back to the frameworks that you've built, you're trying to abstract that, aren't you? You're trying to kind of say, well, the heavy lifting's done for you. We don't, there's some simple tools that can remove the need for 2 decades worth of experience and a PhD and a postdoc and all the rest of it that you have, to get down and really be productive quite quickly with data science.
That's right. If I'm successful, then there's no need for me. I can basically program myself into these
and,
frameworks,
and
and
do podcasts.
that's right.
Exactly.
Exactly. So that's the perfect world where this becomes so simple that all of this knowledge, this deep knowledge, is encapsulated so that a user can just run
Yeah.
and know that they're leveraging all of these decades of experience.
Yeah. Brilliant. I wouldn't mind sort of spending the last minutes of this episode talking about where this gets applied. So we've talked about kind of the theory, I suppose, of massive scale and some of the approaches that you take and the skills needed to sort of develop these kind of applications and then use them. But what's the so what? Like what do we do with all this stuff? What problems can we solve? How can we make the world better because we can deal with massive scale? And in real terms, not where would you like it to be pointed, because I'm sure you have some great aspirations and visions about the kind of problems it can solve. But I mean, genuinely, what kind of use cases have you worked on with this? And I'm just really interested to kind of hear about some of those.
So a great question. We've worked across a number of disciplines. So I'll pick out a few examples.
Great. Perfect.
One
Yeah.
is one is in cybersecurity. So there are advanced persistent threats, often threats to our organizations and countries that develop over long periods of time. And you may be looking for a single packet in your entire network that's a tell for this type of attack.
Right.
And these, for instance, infect supply chains or burrow very deep within our networks. So often we may need to collect up multiple years, maybe even up to 10 years of network traffic to be able to piece together these types of intrusions.
Right.
And so this is one area where we're keeping organizations and even whole nations safer by being able to detect these very long-term threats against our technical resources.
Right.
Another
Fascinating.
area another area would be in medical informatics. We may want to look across patient records beyond what you could do with just a handful of records at one doctor's office, but to be able to look more large scale to try to understand causes of disease, environmental factors, and also be able to understand treatment for those diseases across larger populations. So
Right.
often this requires quite substantial data sets and computing power in the right environments to protect the patient information to be able to understand, for instance, the spread of disease and how to prevent it.
Mm. Did you just on that one, did you get to support or work on any sort of COVID-19 related problems?
We did. We worked on a couple of different areas related to COVID. One was trying to understand in the very early days how to do contact tracing
Mm.
among large populations. And there, the real world problem is much more challenging than when you think about a notion of just contact tracing. Often you have individuals where you have them registered, and what do you do when you can no longer find them again? Their telephone no longer answers, or they disappear from being able to contact. And how do you really do contact tracing based on real world data challenges? So
Right.
we assisted with some of that. We also looked, in fact, we had done work many years ago on other pandemics, for instance, H1N1,
Mm.
the influenza pandemic from a decade ago. We dusted off some old codes for doing this virus propagation and detection and put those into use for COVID as well.
Right. Amazing. Well, it's good to hear that yeah, there's some genuine use cases that this applies to. And I guess though I sort of asked you to not do the pie in the sky, but where can this go? Is there some use case either that you're working on now that are of this kind of massive scale, or where this heads? Is this about supporting space travel or and getting Tesla and Musk's organization to Mars, or is this a bit more, again, a bit more sort of realistic, local based, and industry, like more focused on industry?
Fantastic question. What I want to do, similar to what I've done with democratizing supercomputing and now democratizing analytics, is really democratizing data science. I
Mm.
want anyone around this planet to be able to use data to ask and answer important questions that solve global grand challenges that we face every day on this planet. I
Mm.
think that there are people who can solve some of the hardest problems that we have that may not look like you or me, but they may be somewhere on this planet. Maybe they have very limited resources, but with these types of tools that we can make available, they'll be able to harness the power of these massive data sets to improve the world. And that's really my goal, is to see that data science is democratized, that everyone has equitable access to it to be able to solve the problems that matter most to them.
Nice. And I think you're putting your, this isn't quite the right metaphor, but your money where your mouth is, because you're open sourcing everything you do. This isn't about sort of hiding this away and wrapping it around a software license fee or a software as a service kind of subscription. This is open source. You're putting it on, I think you said GitHub. And is that to enable this? That's for reach, right? That's to get it in front of people.
Correct. I've always believed in open sourcing my research codes with a license that can be used by industry to do development on the code to
Yeah,
make it freely available and open sourced under the appropriate licenses. And I
right.
think that's the way to accelerate most the use of these tools to enable data science at the large scale. And this is something I've done my whole career on GitHub. You'll find my repositories of codes we've developed through many decades of research. And here with the Arcuda framework, this is a really fantastic framework that we think is going to be quite useful. It already has early adopters, and we hope others will come check it out and give it a spin, kick the tires, and see how it works for them.
Brilliant. Well, we've got reach on this podcast from I think 120, 130 countries, and I know a lot of people that listen are in the kind of hands-on data science kind of space. So hopefully, you pick up a few advocates and contributors to your open source code. So, yeah, let's hope we can get you a few more access to a few more people.
That would be great. We'd look forward to it.
Brilliant. Well, I think with that we'll wrap up, David. It's been absolutely fascinating talking to you, an industry, a long-standing industry member, and yeah, influence lots of the technology that everyone takes for granted now. So appreciate that certainly from your past, and appreciate your time in this episode today.
Thank you. Great to talk to you, and I look forward to hearing from your listeners.
Yeah, so do I. Thank you, and thanks everyone for listening. Thank you again to David, and we hope you enjoyed this episode. And I'll talk to you again soon.